Right, morning guys. How we all doing? Looking good. Yeah. I'm actually hiding in that cupboard at the back there. I just got a really bad hair day, so I don't want you to see me. But we're going to move on today. We're going to do some even and odd functions. So certain functions display types of symmetry. So we're going to look at both line symmetry and rotation symmetry, as this can be useful when analyzing the behavior of a function or sketching its graph. Okay, so the more and more we know about a function, and the form that its graph takes, then the easier it is to draw. So this, along with continuity, which I'll do at the end of this slide, are literally the last two parts before we actually start drawing these full functions. Okay, so you don't necessarily have to check this when you are sketching a function, but obviously it's going to tell us more. If we know that it's got any kind of rotational symmetry or line symmetry, then we basically only need to know what half of it looks like. And then we can just draw it in the other half using that symmetry, okay? So we can say that a function f is an even function if f of minus x is equal to f of x for all x in the domain of f. So graphs of even functions display reflectional symmetry across the vertical axes. For example, cos x is an even function. So if you imagine a cos x function across the y-axis, it is reflectional, okay? For an odd function though, so a function f is an odd function if f of minus x is equal to minus f of x for all x in the domain of f. So graphs of odd functions display rotational symmetry of 180 degrees around the origin. So for example, sine x is an odd function, okay? So many functions are neither even nor odd. So you can think of plenty that are neither even nor odd. As I say, it's just if a function actually is even or odd, then it's just going to be easier for us to actually draw. So this could be a separate question in itself. So there's been a few of these in the past. Just prove that if this function is even, prove that this function is not odd. Whatever it is, then I'll show you the process in the example in the next one. Okay. So prove that f of x equals x squared with domain R is an even function. Okay, so what we're basically trying to prove is that f of x is the same as f of minus x, in which case it reflects in the y-axis. Okay, so let x be any real negative number. So you literally just pick any number. So I'm just going to pick minus 2 here, and I'm going to find out what f of minus 2 equals and show that that's the same as f of 2. Okay, which is exactly what I've done in this line. F of minus 2 is going to equal minus 2 squared, which is 4, which is the same as 2 squared. Therefore, it's the same as f of 2. Okay. So what we can say is therefore that f of minus x is equal to minus x squared, which is equal to x squared, which is equal to the function in the first place, f of x. Therefore, f of x equal to x squared is an even function. Okay, and that's literally it. And you can imagine the graph, obviously, of x squared. You knew in the first place, hopefully, that it was an even function because we know it reflects in the y-axis. Okay. So similarly, if we're trying to prove an odd function, so we've got to show that r of t is equal to 2t cubed minus t, with domain R is an odd function. Okay, so let t be any real number. So again, we can just pick a number. I'm not going to pick for this one. Okay, but nonetheless, I'm going to show this straight away from using t's and minus t's. Okay, but you could do this with proving numbers. So r of minus t, is equal to 2 times by minus t cubed minus t, which in itself equals minus 2t cubed. Obviously, minus t cubed is just minus t cubed. Okay, so times by 2 becomes minus 2t cubed. Minus t becomes plus t, and that is the same as minus 2t cubed minus t, okay, which is equal to minus the whole function minus r of t. So that in itself proves that r of t is an odd function, okay? And just in case you're wondering, that's what it looks like. And you can see hopefully there that it does rotate 180 degrees around the origin, okay? So sometimes you're actually asked to show that it's not even or odd. Okay, so you might be given a function and be asked to prove that it's not even or odd. Okay, so to do this, we must produce an element a in the domain of f such that f of minus a is not equal to f of a. And likewise, if you're trying to show that a function is not odd, you must produce an element a in the domain of f such that f of minus a does not equal minus f of a. Okay, so just the opposite of what we're just doing. We're trying to prove, obviously, that it's not even or odd by basically proving in the same way. Okay, so if 0 is an element of the domain of the function f, then for f to be odd, it must be the case that f of 0 equals 0. So this is a nice, easy one to prove, since otherwise the graph of f would not display rotational symmetry about the origin. Okay, therefore, a quick way to show a function f is not odd is to show that f of 0 is not equal to 0. Okay, and that's exactly what I'm going to do here. So we're going to show that the function s of t equal to t squared minus 3t plus 2 is neither even nor odd. Okay, so basically just shoving a 0 into the function. S of 0 is equal to 0 squared minus 3 times 0 plus 2, which is equal to 2, which is not equal to 0. Therein, s cannot be an odd function. Okay, so that's proving that it's not odd. Proving that it's not even is the same idea. We're basically just trying to show that in this case, at least, s of minus 1 is not equal to s of 1. Okay, so s of minus 1 will be minus 1 squared minus 3 times by minus 1 plus 2, which is equal to 6. Okay, s of 1 is equal to 1 squared minus 3 times 1 plus 2, which is equal to 0. And since 6 does not equal 0, s cannot be an even function. Okay. So the two types of questions that you might get there, as I say, show that it's even, show that it's odd, or show that it's neither. Okay, but as I say, when we get on to actually drawing the graphs of these functions, it just helps to show that it's even or odd in terms of actually drawing it at the end of it all. Okay. So continuity is the final part of this. As I say, once we get this done, we're actually drawing these equations from scratch. Okay, so f of x, if f of x, is a real value function with domain D, then f is continuous at the point where c is in D if the limit of the function f of x as x tends to c is equal to f of c. Okay, if f is continuous at every point in its domain, we say that f is continuous. Okay, if this condition does not hold at some point for C and D, we call C a point of discontinuity, yeah, that's it, and say f is discontinuous or not continuous. Right, if f of x equals 1 over x, that's what the graph looks like, okay, and f of x is not defined when x is equal to 0, therefore f of x is discontinuous, okay. So virtually the same as when we're doing asymptotes. If we can basically prove an asymptote, a vertical asymptote like this, and show that obviously it's undefined for a certain point, i.e. x equal to 0 in this case, then we can say that f of x is discontinuous. So we'd be proving the asymptotes in when we're drawing the graph of the function anyway, but again, it just gives us a point at which we don't have a value for when we're actually drawing this. Okay, anyone got any questions? Okay, good. Okay, if you do genuinely have any questions, I'm literally going to be doing nothing for the next week. So you can pop them on Teams. I'm sure Mrs. Dower would allow you to use your phones and pop them on Teams as you're in class. And obviously I know when you're in class, so I can be on Teams, ready and waiting to answer your call. Okay, but have fun, guys, and I'll see you again on Friday.